Suppose we have a rectangle of wire here. We'll make this side length A, this side length B. And I have a current flowing through it clockwise. No particular reason. It's either clockwise or counterclockwise. And into this, I am going to put a magnetic field. So let's have the magnetic field going off to the right. I have a current, therefore, since it's going clockwise, it's going up right here, it's going to the left right there, and it's going down right there. Well, in terms of the force on the segments of wires, on this segment of wire right here, the current is in the same direction as the magnetic field. And if you recall, it's I delta X or delta L cross B. I'll probably stick with L, is the force. And if they're in the same direction, then there's no force. So there's no force on this top level. Let's set up a coordinate system. I, J, and K coming out. So in this section right here, my cross product is my current is going in the negative J direction, cross with my magnetic field. I cross J is K. J cross I is negative K, but that negative sign makes this K. So there's a force on this coming out. Down here, delta L and B are anti-parallel, and therefore there's no force on this section. And over here, it's in the opposite direction of that current flow there, and the force will be in the opposite direction. So what I have is I have this group of wire here being pushed up on the right and down on the left, and so in essence it will rotate. There's torque involved. Matter of fact, it'll rotate about the center. So I have my axis right here, and I'm pushing up on that side and down on that side. I know that the force is going to be equal to the current times the length times the strength of the magnetic field in the K direction. The force on this side is IAB in the negative K direction. This distance right here is 1/2 B. And why does that matter? Because we're doing torque. If you recall, torque is R cross F. So my R here is, they are perpendicular to each other, so the magnitude of the torque is just the product of the magnitudes. But this is in the I direction, so this becomes I cross K. R cross F, I cross K, so it's in the I direction, that's negative I hat. I cross K is negative J, and so we have torque, my total torque is the torque on the right side plus the torque on the left side. And on the right side, it is 1/2 B times I little a B, and we established in the negative J direction. Plus on the left side, so this is negative I cross negative K. The negatives cancel out, and we're left with I cross K, which is negative J. So minus 1/2 B times IAB. They're in the same direction, which makes sense that they are sort of both causing it to rotate. So the torque acting on it is, well, I got half here and half there, so I add it together. So I have B, little b, I, A, big B in the negative J hat direction. Or rearranging, negative little a, little b, I, big B. Now, this a times little b, that's just the area. So that's equal to negative area times I times B, J hat. And this area times the current has a special name. This is known as the magnetic moment. And of course, what letter do they use? They use mu. And so we have mu times B, and we can generalize it that the torque is equal to mu cross B. The direction of mu is the direction of the magnetic field in the middle. So let's make sure that works here. Since the current is going clockwise, the direction of the magnetic field in the middle is down. So that would be negative K. Cross the magnetic field, which is in the I direction. K cross I is J. And so that puts it in the negative J direction, is what we have right here. But this is the generalized formula.